Okay, we're going to continue on here at chapter 13 and chemical equilibrium. So in chapter 13, we were talking about chemical equilibrium, which, as we talked about, involves reversible reactions. And when we do have reversible reactions, once again, it does go in two directions. Again, the forward direction and then the reverse direction, heading in that direction there. And when we do reach chemical equilibrium, as we talked about, what that means, again, is it is not an even amount of everybody on each side or anything like that. We really are talking about the rates here, and we're talking about the rate of the forward reaction will equal the rate of the reverse reaction. So as we talked about, essentially what that does is when it reaches chemical equilibrium, it pretty much will lock everybody into place in terms of their concentrations or pressures that we might be dealing with. And basically, it kind of looks like there's not much changing at that point, because just as fast as you kind of go in the forward direction, you will be going in the reverse direction. So it's able to really maintain their concentrations when it does reach equilibrium. There is an expression that relates the products to the reactants, which is the equilibrium constant, and that really is the concentration of the products divided by the concentration of the reactants. So for the one above, we could write C to the C, D to the D, divided by A to the A, and B to the B. Here we do use the coefficients as the exponents when we write the equilibrium expression. As we talked about at the end, as we'll talk about here again, yeah, there's really kind of two things you do not include. And that is anything that is a solid or really a pure liquid does not get included in the equilibrium expression. They're really not participating in the equilibrium expression. The pure liquid basically remains constant, its concentration over the whole time. And something that's a solid is just kind of sitting there hanging out, not really participating. That pretty much means that you do include what's left there, which is things that are aqueous and things that are gas. When we write a K value for an expression like this, where we use concentrations, we sometimes refer to as Kc. The Kp can also be written in situations where we have gases, and it would be done the same way. We would take the partial pressures of our products divided by the partial pressures of our reactants. Kc usually does not equal Kp in terms of numerical value, but they both do tell you kind of the same thing. And as we talked about last time, if we have a large value of K, that means that when we reach equilibrium, we should mainly expect to have products present. If we have a small value of K, that means when we reach equilibrium, we should mainly expect to have reactants present. A large value is really anything sort of 1 and above. So above 1, there's sort of considered large. And anything less than that obviously is considered on the small side. There is a formula that we saw as well that allows us to go from one to the next here. And that is the Kp is equal to the Kc times R, which is the gas constant like we use in the ideal gas law. And T is our temperature in Kelvin. Delta N, as we talked about, is the change in the number of moles of gases. So that is your product gas moles minus your reactant gas moles. And as we talked about, it's really important to make sure you do it that way, because mathematically speaking, if you do get a negative number there, it is going to be different math than if it was a positive number. So it's really important. Any questions on any of that stuff there we talked about last time? All right. So I think we left off with this example, perhaps. So let's take a few minutes here. The equilibrium concentrations for the reaction of carbon monoxide to molecular chlorine is as follows. CO is 0.012, Cl2 is 0.054, and COCl2 is 0.14. calculate both the Kc and the Kp value in this case. Let's take a couple minutes to see what you come up with. Okay, let's take a look and see how you're doing. So in this particular case, we are given the equilibrium concentrations of everybody that's there. We do want to find Kc and Kp. It would make sense to find which one first in this case. Kc, since we have the concentrations. So that definitely is where we would want to start. So our Kc would again be our products, which in this case would be CO, Cl2, divided by the concentration of CO and the Cl2, which is our reactants. Popping in our numbers there, we get 0.14 divided by 0.012 and 0.054. So if we pop that into the old trusty calculator there, we yield a 216. We're still chemists, we'll maybe do a 220 on some sig fig action maybe and stuff like that. Any questions on that one there? Obviously they all have 2 sig, so we could go with 220. 216 obviously is what you get on the calculator there. That is our Kc value. We then could use our Kc value to calculate the Kp value using that formula that basically relates the two. And that formula again is that the Kp is equal to the Kc RT delta N in this case. And we do want to figure out delta N. So delta N is our moles of our products, which is 1, right? Just one gas there. Minus our reactants, which is 1 there and 1 there, makes 2, which means we're looking at again here a -1 for our delta N. Any questions on that there? We also need to do a little conversion of our temperature. So we need to take our 74 there, add a 273 to it to take it into Kelvin. And that's going to give us a 347 for our Kelvin. And now I think we have everything that we need to calculate the Kp. Kp would be our Kc. I'll use the 220 number there, 0.08206 times our 347 to the -1. Just so we're clear on the math, you should do the stuff inside first, yes, and then take it to the -1 and then multiply it by the 220. So if you do that, 0.08206 times 347, take it to the -1, which is basically taking 1 divided by it, yields us a 220 and approximately 0.0351187, which we then will multiply by 220 and yield us a Kp value of 7.7 in this case. Any questions on that there? Plug in 216, then you don't get 7.7, you get 7.6 maybe? Yeah, something like that. You should, again, since it is a chemistry class, try to shoot the right sig figs. Would be good. Yeah. Other questions on that? So as we see here in this example and how it usually is, the Kp and the Kc usually don't equal the same number. They can in certain cases, but they usually will not equal the same number. But they both tell us really the same thing here. Are these considered large or small values of K? These are considered large value of K, which means we should expect to mainly have products when we reach equilibrium. And if we look at the concentration, we got more concentration of our product than our reactants. So that all sort of makes sense. So they're both large values. They both tell us we should have products at equilibrium. Any questions on any of that there? Yes, sir. R is the gas constant. So it's the same one that you would use for the ideal gas law, PV equals nRT. So 0.08206 is a number that was like beat in my head when I was younger. So I always use it. But a lot of times nowadays, they will use the rounded number like 0.0821, which is perfectly fine too. So if you want to use that one, but that's the R one. So R has a few different values, obviously. but R is 0.08206, and that's really liters, atmosphere, Kelvin, mole. Or again, you could use the 0.0821, or like on the quiz, the one that involves energy, right? Is that one there, the 8.314 version of it, which you'd want to use anytime you're doing any type of energy. This is really, since the KP is really related to gas, you want to use the one that you like you would use in the ideal gas law. Other questions? Yeah. There are not. So as we talked about before, the equilibrium value, the K value does not have units. Historically, they don't have units. I will say occasionally you find people that'll put units on it, but you shouldn't really put units. So it's really just a number, and it will either sort of tell you large number or small number. So for us, we don't really put units on it. Very rarely you'll see people kind of include the units. Yeah. Was that your same question or? Yeah, so again, in this situation, if you're calculating K like we did here, you don't necessarily have to put the units in. You can if you want. At the end, always make it clear for us, and in most situations, pretty much 99.9% of situations, if you're asked to calculate K or give a K value, it should just be a number, no units associated with it. Other questions? All right, so let's try another one here. The equilibrium constant Kp for this reaction is 158 at 1,000 Kelvin. The equilibrium pressures of O2, what is the equilibrium pressure of O2 if P, that first one actually should be NO2, that first one there. That might make it easier. The second one will be NO. So I think you need to add the 2 there. Okay, it's the NO2, that one. All right, so take a minute, see what you come up with here. So let's take a look here. So in this case, obviously we're given the KP and we do have some pressures and we're looking for pressures. So that would be a good place to start. We'll start with our KP expression, with once again would be products over reactants. So it's going to be the partial pressure. We are going to square it of the NO times the partial pressure of O2 divided by the partial pressure, once again going to be squared of the NO2 because of the coefficient. That will actually equal 158 in this case. So if we just put our numbers in here, we get basically that the NO was 0.27 squared times the partial pressure of O2 divided by our NO2, which was 0.4, also going to be squared in this case. We are going to multiply that to the other side, right? And then come back and divide by the 0.27. So we're going to take 158 times 0.4 squared. That gets us 25.28 is equal to 0.27 squared, PO2. We're then going to divide, right? So we'll divide that by 0.270, also squared. Gets us a pressure of O2 of 347. Should this have a unit? This should have a unit since it is a pressure, so the unit would be the same as everybody else, which would be atmospheres in this particular case. Any question on that one there? 158 is a large value of K, right? Which means we should mainly have products at equilibrium, and O2 is a product, so it definitely has a pretty high pressure at equilibrium, which means you probably have a lot of O2 flying around at that point. Any questions on that there? All right, so we talked about homogeneous equilibrium. Heterogeneous equilibrium is an equilibrium where everybody might not be in the same state. So in this case, we got some solid, we have some gas. We could write our Kc like normal. Once again, the solid here are really not participating in much what's going on. So the correct Kc expression for this guy would actually just be the concentration of CO2. And if we want to write a Kp, which we could, since this is a gas, we would write the partial pressure of CO2. So typically speaking, anything, as I mentioned before, like solids or liquids, they are not included in the equilibrium. You could kind of think of it like this. A solid is just kind of sitting there, right? The only way for a solid to sort of participate is it would have to dissolve, perhaps, right? Or go into the gas phase, which means it's no longer a solid, it's a gas or a aqueous guy. So solids really do not have any effect on the equilibrium. So once again, it is just aqueous things, solutions, and gases that should be included in your equilibrium expression. As you can see here, again, they're just kind of sitting there, not much happening with really what's going on, which is all these guys basically flying around in that equilibrium. Do they change amounts? They can change amounts, but overall, they really don't make a difference along the way here. All right, so let's talk a little bit about this one here. Consider the following. The partial pressures of each gas is 0.265. Calculate the Kp and the Kc for this reaction. Look, here's just getting towards the end here. Once again, we're looking for both. So in this case, we are giving pressures, so it would make sense to start with the Kp first. We would write our Kp expression here. Partial pressure of NH3 times the partial pressure of H2S. Do I include the guy here? I do not. Again, it's a solid, so we would not include it. By the way, if we had, say, something like this, actually, backwards, try that again. So let's do, so if we had something like this, actually, heading both directions, how would we write the equilibrium expression for it? Since we don't include the solid, right, it would be 1 over, right, say the concentration of A, or 1 over the partial pressure of A. So if you happen to come across rarity, but if you happen to come across maybe on the product side, they're all maybe solid or liquids, you would do 1 over basically the reactants would be how you write the expression. So in this particular case here, we could pop in our pressure, which basically is just this squared here. So that would get us 0.265 squared. Gets us a 7.02 times 10 to the minus 2 as our Kp value there. Any question on that one there? Now that we have the Kp, we could again use that formula to go from the Kp back to the Kc, which once again is Kp is equal to Kc RT delta N. We'll calculate our delta N in this case, which would be 2 minus 0, which would be 2. 1 gas there, 2 gases there, and nothing on the reactant side. Our temperature here that I scribbled all over is already in Kelvin, so that is good to go. And I think that's everything in this case. So that would get us 7.02 times 10 to the minus 2 equals the Kc, our R, our temperature, which is 295. And once again, we're going to square it. I'm going to basically kind of clean up everything right there and get me a number. So that is going to be 0.08206 times 295. We're going to square it. Going to give us 7.02 times 10 to the minus 2 equals Kc times, if I could read my calculator, I think it says 586.012739 as I don't round here. I'm then going to divide that obviously to the other side, and that would get me a Kc value of, looks like we'll call it 1.20 times 10 to the 1, 2, 3, 4 minus 4. So 1.20 times 10 to the minus 4. Any questions on that calculation there? These K values here are large or small? Small. So we would mainly expect to have reactants in this case, which means in this case, not a lot of that solid is going to basically go through a decomposition reaction and decompose. So, yes. Is the moles of products minus reactant, but they're just the gases. So only the gases involved in that. So that's what the delta M there is, basically the moles of the gases. So we got 1 for the NH3 and we got 1 for the H2S. Basically just add up the coefficients for anything with a G, basically. And then on the reactant side, obviously there's no gases. So that was where the 0 came from. Other questions? Yeah. Would I start with? There would be absolutely positively no way to do that because you don't have any concentrations. So the only way you could solve for Kc is you would need some concentrations. So you can't do that. Yeah. Yep. Other questions? All right. We'll lay it up there for today.